Buenas noches, señoras y señores, and I apologize that that's pretty much the last that I will say in Spanish. I will mangle Spanish a little bit more in the next slide, but I'm grateful to the organizers that you've have translation, and I'm very excited to be here today and to tell you about the deep sea and how the discovery of incredible communities of animals that I'll be showing you have completely revolutionized our understanding of life on Earth. But because we're trying to combine science and music and emotions, I'd like to start with a poem by the very famous Chilean poet Pablo Neruda, who had a very emotional relationship to the sea and wrote, "Necesito del mar porque me enseña. No sé si aprendo música o ciencia, conciencia, sorry. No sé si es ola sola o ser profundo." These are just the first three lines. And again, apologies that my Spanish is not perfect. But I think what moves me in this is the love that Pablo Neruda has to the sea. And I'll tell you a little bit about how I came to work in the deep sea and my own emotions. And I grew up in New York City and on the oceans and would spend 2 months in the summer there. And so I knew very early on that I wanted to be a marine biologist. Not because I was very good in biology in school. Quite the contrary, it was my worst subject, and I nearly flunked it. But I had this very romantic idea that I would go in the morning and diving, and only along beautiful coral reefs. The water would be at least 25 degrees warm, never colder, because I don't like that. And then maybe in the afternoon, I would work a little bit in the lab on samples. And this was going to be my life as a marine biologist. The reality of my master's thesis, which I did in northern Germany, was very different. So I had to work on samples that were in the mud. It was winter time. I would sink into the mud all the way up to here, and the mud would get into everything. And so I definitely saw there was a discrepancy between what I thought, what my dreams were, and reality. And so I decided for my PhD, I need a different subject. And a professor suggested to me I could work on little teeny tiny marine worms that don't have a mouth, that don't have a gut, and that you can barely see. They are at most 2 centimeters long, only 0.5 millimeter wide. And once again, there was quite a discrepancy between my dreams and what I was thinking about, and why would I want to dedicate my life to working on little worms that you can't even see, because like most marine biologists, I wanted to work on whales and dolphins or on coral reefs. But then the professor told me where these worms occur, where you can find them. And they occur mainly in the tropics and the subtropics. So what you do is you go out where there are coral reefs, where there are seagrass meadows, and you stir up the sediment, and this is where you can find them. And so my very first trip, I went to Belize. The Smithsonian has a station there, and collected them and decided that this was definitely something that I wanted to do, but not only because of the beautiful environment, but because I was fascinated by their biology. How can you have live without a mouth, without a gut, and still get nutrition? And the answer is because of symbiosis. They live in symbiosis with bacteria. And so let me very briefly explain what symbiosis is. Symbiosis is defined as the coexistence, the intimate and physical living together of different species. And it was discovered by a guy called Nicole Dubilier, and he was working on lichens. And lichens, he realized, are actually two different species. There's the fungus side and the algae side. And I like to emphasize that for humans, we think about symbiosis very differently in psychology, because we think about symbiotic relationships, possibly with our partner or with our children, or sometimes not so symbiotic, but that's between the same species. So in biology, it really matters that it's different species that have found a way to form a holobiont together. For a long time, biologists, particularly evolutionary biologists, thought that life on Earth evolved through competition, through survival of the fittest. But we know now that cooperation, that symbiosis, was essential for the diversity of life that we have on Earth. You wouldn't be sitting here and being able to breathe if you didn't have mitochondria in every single cell. And these mitochondria, they're power cells that allow you to breathe oxygen, and they originated from way back 1.5 billion years ago, a symbiosis between two different microorganisms. So you have to be grateful that you can be here today because of just something as simple as two microorganisms coming together. On Earth or on land, symbioses have been well studied because it's easy for researchers to reach land, but the greatest diversity of species is in the ocean. And the oceans cover, as most of you might know, 70% of our Earth. What we know about and know well are the symbioses between corals and algae, and there, as many of you might have already seen, the depressing pictures as the oceans are warming, they're losing their symbiotic bacteria, they're bleaching. And so you can also see how a symbiosis, when it's endangered, a whole ecosystem can then die. So it's another example of the central role that symbiosis plays. The way coral symbioses work is it's the sunlight. The coral is an animal, and so it can't gain energy from the sun, from primary production. It needs its algae. The algae are taking the sun as an energy source, and then they're fixing CO2 out of the seawater, and that CO2, they're changing, they're reducing it, they're making sugars out of it and carbohydrates, and they're feeding their host with it. But that is in shallow waters, and most of the oceans is deep. It's not, light only penetrates 200 meters down. But about 80% of the oceans is the deep sea, where it's dark, where there is no light. And we estimate that over 50% of the animals that are in the deep sea are unknown to science, are unknown to us. So every time we go out on a research cruise, we discover literally 10 to hundreds of thousands of new animal species. And for microbes, we estimate that we at best know 1 to 2%. And of the 240,000 species of animal species that have been described so far, we estimate there must be easily at least 10 to 100 million that we still need to describe. So I think it makes it very clear why the incredible diversity that we have in the oceans and how much we have to discover. And one of the most amazing discoveries that we made was the discovery of gigantic animal communities thriving in 3,000 meters water depth, 3 kilometers below the surface in absolute darkness. The reason researchers didn't know about these animal communities, they thought the deep sea is a desert. I'll show you some images of what it looks like. Most of the deep sea was because they couldn't get to the bottom of the oceans. The submersibles were used by the military, but not by research. And it was the Alvin that was actually used by the US military, the US Navy, that was then donated to research that allowed the researchers then to go to the bottom of the ocean. The geologists had known that there were hot springs at the bottom of the ocean, and this was because they would put a temperature, a thermometer down on a long string, let's just call it a string, and measure very minimal increases in temperature. And they knew this because mapping of the deep ocean had already shown that there were mountain ridges at the bottom of the seafloor, and in the 60s, the theory of plate tectonics, that the ocean's plates and the Earth's plates are moving apart, was already accepted. And so what is happening at hydrothermal vents at these mid-ocean ridges is that the Earth's plates, the ocean's plates, are moving apart, and there's hot magma that is rising up from the center of the Earth, and that is forming new ocean floor. And we estimate that the growth of ocean floor is about as fast as your fingernails grow. So you can, oh, that is not good, but there might be somebody back there that is trying to get it back again. And we estimate in very fast-spreading ridges, you would have to have very fast-growing fingernails, and there are ridges that move very slowly. So as you get older, everything grows more slowly. Actually, nothing grows anymore. But anyway, so this is also, there are differences in how they grow. So we need instruments that allow us to get to the sea floor and to look at it correctly. And what you see here are instruments like an autonomous underwater vehicle that is not tethered to a ship, and here a remote operated vehicle that I'll show you in a second. But I want to also give you an impression of how difficult it is to see the seafloor. This is on the top are satellite images that we can do and easily see. And when you use satellite imagery to look, for example, at the Gulf of Mexico, then this is the resolution that you can get. If you use an echo sounder from a ship, then you can get a resolution of about 6 kilometers, which would be comparable to what you see here in a resolution of the gigantic city of Berlin. But of course, that's not going to tell you anything about the seafloor and what you really want to know. And so you need to go to the bottom of the sea to actually map the seafloor. Here in a resolution, what you're looking at are these fantastic asphalt volcanoes. They're spewing asphalt and tar in the Gulf of Mexico to get this kind of resolution. And then if you really want to sample the animals, you need to go down there and collect them with a submersible. Okay, there are 2 types of submersibles that we use, and the Alvin that I presented is a manned submersible. There's 1 pilot and 2 scientists, and that's it. And that's all that fit in the submersible. What that means is that only the 2 scientists working with the pilot during a dive that can be 12 hours are doing the science. They can communicate with the ship, but it's slow. This is why now in science we prefer to work with remotely operated vehicles. So many of them are tethered to the ship with a cable, and the scientists and the pilots, what you see here, this is the control van from which the ROV is flown. So they're pilots, they call themselves pilots, and they fly the ROV. They're very proud of their, and it is difficult to do this well. They need particularly very good video capabilities because they're looking at a 2D screen, but they have to work in 3D. And they have to manipulate the arms of the ROV with tiny little joysticks that you can't actually see well here, which is sometimes quite amusing because the pilots also need to do a lot of heavy lifting. These are very big guys, but then they have to work with this little joystick to move the arm very carefully, and some of them do not enjoy it, but others like it a lot. And what you can imagine here is it's real time. You're getting the data immediately as you're down there. So a lot of scientists can work with the pilots together immediately and say, oh, I don't want that muscle, I want that muscle, which some pilots do not like. So what happened when the hydrothermal vents were discovered? Let's go back again to the history of the discovery. It was assumed at that time that all of the deep sea, the ocean floor, is a desert. And these images that you see here are actually very exciting images of the deep sea because you can see something like a sea cucumber here or a sea star here, a sea feather. But really, most of it is a desert. And the reason is because there's no primary production. So if animals need to eat plants, and they need that for the primary production. And it comes from sunlight. And you have on the oceans, you have it from algae that are using the sunlight, and they're producing a lot of oxygen. Every second breath that you breathe is probably produced by marine algae. And on land, it's plants and trees. All of that production from the sunlight is all that there is for the plants, for the animals on the seafloor to get down there, and very little makes it down because there are all these other animals in the water column that are eating up all the algae that are sinking. So now imagine you're in the Alvin and you have no idea, you're looking for the hot springs, and you're going along, you start to see lava that has come out, and you're seeing a lot of nothing. And then all of a sudden, and there are videos of the pilots, this incredible animal communities pop up out of nowhere, or seemingly out of nowhere. What you're seeing here with the red head is the plume of giant tube worms. They don't have a mouth, they don't have a gut, they're full of symbiotic bacteria. You can see the mussels down here. Here you're zooming in, and one knows from the videos that were there that the geologists that were at the bottom of the seafloor, they radio cabled up to the ship and they said, isn't the deep sea supposed to be a desert? And they had one biologist on this cruise, and it was a student, and the student said, yeah. And the geologist said, because there are a lot of animals down here. So this was really what I say, the last major discovery of an ecosystem on Earth that we had no idea exists. So where does the food, how are they gaining their energy if there's no light energy? So they're gaining their energy from a process. It's the only other way that we can have primary production next to light, through a process that is called chemosynthesis. And what it is reduced compounds that are coming from the seawater that is getting heated up in the magma chamber. It gets as hot as 400 degrees, is coming out of these chimneys, and it's full of hydrogen sulfide. You might be familiar, that's the smell of rotten eggs. If you ever go out to a beach and you dig a little and it smells like rotten eggs, that's hydrogen sulfide. If you put that together with oxygen, it's going to give you a lot of energy. Same with methane, and hydrogen is down here. When these incredible metal-rich fluids that are coming out at 400 degrees hit the seawater, which is only 2 degrees, they precipitate and they fall out, and they form these incredible chimneys, these black smokers that you see at hydrothermal vents here. And this is Alvin down there in proportion to those chimneys, how high they can grow. And they estimate from growth rates that they can grow as much as 30 centimeters per day from all of the iron sulfides and the metal sulfides that are precipitating out and building these really remarkable and incredible chimneys. So the photosynthesis gives the energy of the light for fixing CO2. And in chemosynthesis, what we have is chemical energy from the sulfide or the methane that is being oxidized with oxygen, and where the symbiotic bacteria are fixing CO2 and feeding their hosts. We're animals, we can't fix CO2. We can't do primary production. So that is why it's such an advantage for the animals down there to live in symbiosis. So this is really what revolutionized our understanding of the energy forms on life that can fuel animal communities. Up until the discovery of the vents, it was assumed if there wasn't light, you wouldn't have animal communities like this. And now we know you can have chemosynthesis, which can fuel these communities. And the biomass, which is the amount of animals that are there per square meter, is incredible. It's as much as in tropical rainforests or in coral reefs. And all of it is based on symbiosis. If there wasn't symbiosis, you would not have these communities. The symbionts, the bacteria, are giving their host food, but the host is also giving something back. Remember the big red plumes of the tube worms? That's blood, hemoglobin, that is in the tip of the worms, and they're using that hemoglobin not only for their own breathing, to breathe and respire oxygen, but also to fix CO2 and even hydrogen sulfide, which is normally hydrogen sulfide is toxic for animals and for the blood. So very impressive what they do, and they've modified their entire guts, normally where they would have a gut, and it's full of blood vessels to supply their symbiotic bacteria. And what is also amazing is that the animals, although they're so dependent, these gutless worms, on the symbiotic bacteria, they have to acquire them every generation again from the environment. And that means although there are millions and millions of bacteria in the environment, they have to find a way to communicate with their symbiont and say, I will let you get in and infect me, but you, all the rest of the millions, have to stay out. So very, very impressive biology going on. Okay, in my lab, we work on the symbioses in mussels. And now I'll show you a video showing you what it's like when we work on them and what it's like when we're at sea. Because of the symbioses, the biomass, again, the amount of mussels per square meter is 2 to 3 to 5 times higher than it would be in shallow water mussels, for example, here off the coast of Chile, of Mytilus chilensis. And that's because shallow water mussels, they have to work super hard. They're filtering that water. They have to get the algae out of it. And here at the bottom of the sea, they can tell their symbionts, feed me. They have lots of energy down there, and that's why they can get these, why they can form such large communities. Okay, so this is what it looks like when we do a research cruise. This is a recent research cruise to the mid-Atlantic. You're going to see Bremen, where my institute is, and we're going to zoom out from the institute. I think you might have to click on the video, because if I click, right, can you click on the screen and get the video? Yep, thank you. Oh, it's such a nice video. When you click on it, it worked when we practiced this just before, of course. Not going to work? What about what you have on the stick that has a bad format, but you could switch and then go back so that we can at least, would that work? Okay. Improvising is all. The format is going to be a little bit weird because we were struggling with the format as well. But what you're going to see is a research cruise that we go with a German research vessel that about 35 scientists fit on the vessel. And then we have a crew of about 50 that are both navigators and everything that you need to keep a ship of about 100 meters running and going. And we have it's working? I don't see the film. There we go. Okay, great. Wonderful. Okay, so that was Bremen, if you saw it very quickly. You didn't miss much, I'm sorry. But this is the Mid-Atlantic Ridge, one of the longest mountain ridges on Earth. And it's across the entire Atlantic. We went to 4 sites called Logachev, Semenov, Ironevsky, and Ashatse. They were discovered by Russians. Whoever discovers a hydrothermal vent gets to name them. So this is why the names are very different. What you see here is the ROV, which is off the stern of the boat, is now being deployed into the water. This is the most critical moment where it's released, and then on the cable there. The cable supplies it with power, but also there's a glass fiber cable so that we can, in real time, have the data that we want to see on the ship. What you're seeing now is what the camera of the ROV is seeing, which we would see on the ship. As you get closer to the hydrothermal vents, you start to see what we call shimmering water. It's the hot water that is mixing with the cold water that is there and is causing that shimmering. When you hit these mussel beds, the biomass is just mind-blowing. It really, every time I go on a cruise, I see it and I get excited about it. And it creates environments for other animals to live. The black smokers are impressive. I had the great fortune of being on a cruise where we measured the highest temperatures on Earth. They were 413 degrees, the water that was coming out of these black smokers, or 450, I have to go back and look at it, but the highest that have been measured. And so we need very special instruments to sample these hot fluids and to collect the gases, and also to keep the gases in a titanium container that is gas tight, because when we bring it up, so it doesn't expand to the point where we wouldn't actually have all the gases. What you see here are incredible shrimp. They've lost their eyes, but in the back, they now have an eye spot, and we think that it enables them to detect hot temperatures. But they're not always good at it. Sometimes you see a whole bunch of cooked shrimp at the bottom of a hot smoker because they didn't watch out. Here come the mussels that we work on, and just like shallow water mussels, they have an opening and exhalant siphon. What you see now is we were just sitting in the container with the pilots, and here we did a very exciting experiment. For us exciting, here you see this little arm that he's manipulating the huge arm of the ROV with, and we wanted to know if we fix the mussels on the sea floor, will it make a difference versus bringing them up for 3 kilometers? Can we fix them on the seafloor? So we actually had the pilots taking single mussels, don't squish them, only take them very carefully and put them in the little pot over here. We had to give them a lot of beer to make them happy at night. What you see here is that we take the mussels and put them in nets and move them away from the venting because we want to know what happens. Do they lose their symbionts or not? We have a lot of instruments, so we also work with elevators. We call them elevators. We put the extra instruments that the ROV can't carry onto these elevators, and then the ROV will go over and work with them and put it back on the elevator. So that's on a different line. Usually we do about 12-hour dives. And when the ROV comes up, I love the light when you can see it in the dark when it's coming up. It's been a long day. We start the dive with pre-checks at 6 in the morning. That part the scientists are not involved in, but then we're working with the pilots very carefully to get our samples. We're super excited when the ROV comes up because we really, really want to get our mussels and animals as quickly as possible. And here you see us, we're literally racing to finally get our samples and get them quickly. And here, one of the experiments we did was let's take mussels that we bring up live from the seafloor and fix them then so that we can look at them afterwards. And let's also take the mussels that we fixed on the seafloor and compare them whether it makes a difference or not. Now you're going to see an animation. We're cutting into the mussel, and you can see the foot tissue, and now we're going to switch to a computer tomography image, just like when you go to the hospital and have to have a CT done. This is what a CT can do with a mussel about this size. And it starts sectioning through the mussel, through the shell, layer for layer, just like it would in your body when you're having something looked at. And what you see here in the brown in the middle are big, big fleshy gills. And those gills are where the symbionts sit. And they're greatly enlarged compared to non-symbiotic mussels. So this is now a gill. It's made out of thousands and thousands of leaf-like filaments, they're called. And now you're going to see a cross-section that we do and imaging methods that we use under a microscope so that we can actually see where the symbiotic bacteria sit using higher and higher resolution. And so when you compare how many symbionts, which we're calling inhabitants in an 8-centimeter mussel, to how many inhabitants you have in Concepcion, then what you can see is the mussel has a lot more inhabitants per square meter than in Concepcion. So it gives you an idea of how packed they are inside of that mussel. And that's all because the mussel has increased the surface area in which the symbionts sit. What still amazes me is the diversity of chemosynthetic habitats. And one of my favorite environments are whale falls. So when whales die, they sink to the bottom of the sea, and the meat is eaten very quickly. Within just a few weeks to months, sharks will go down and eat up all the meat. But their bones are full of oil, and that oil is degraded by bacteria, and what happens is a lot of hydrogen sulfide then develops. It's like anything that rots, you know that Well, hopefully you don't know it too often from your food supplies that are rotting. And that creates an environment in which chemosynthetic symbioses can thrive. But what is truly amazing is that these types of symbioses also occur in shallow water. So what we like to say in our backyards, where we can go easily, like I showed, and now we're coming back to the gutless worms, they're also living from chemosynthetic bacteria. And zoologists for hundreds of years knew about animals that didn't have a mouth or a gut, and they said, oh, they must be gaining their nutrition from taking up dissolved organic material. Only after the giant tube worms were discovered in the deep sea did the zoologists go back to their shallow water animals and say, oh, they have the same type of symbioses. So it's a good example of, you sometimes don't see a single tree in the forest until you understand the forest more comprehensively. Chile has some amazing chemosynthetic habitats that are still under-researched. It has an amazing geographic location, which you know also from tsunamis and from earthquakes are a problem, but you've got the only place on Earth where you've got a spreading ridge here that is being subducted underneath the plate. So interesting both geologically and biologically. But you've also got methane seeps that occur, 70 kilometers from the coast. So that's only 3 hours away, which are full of symbiotic fauna and animals. But also our little gutless worms, they're not only in beautiful tropical coral reefs, but also in 300-meter water depth in upwelling regions off the coast of Chile and Peru, where you've got a lot of hydrogen sulfide from all the algae raining down and rotting. One note about the dangers that these incredibly unique ecosystems face. Global warming and ocean warming is particularly a problem in shallow waters, less so at the moment in the deep sea. One of the biggest worries that we have is the interest in deep sea mining. And what looks very nice actually here on the image and doesn't look very destructive is very, very destructive for these ecosystems. They're very fragile. There's a ton of sediment that gets sucked up also when you try to mine them, and all of that goes into the water column. So there's a lot that we're very worried about with deep sea mining. So this is what the instruments looks like, just to, it looks nice in a cartoon, but then stand next to an instrument like that and think about what it is going to do to these fragile ecosystems and chimneys, then you get an idea. And I think Chileans can be very proud that they were one of the first to sign a moratorium on mining these deep sea ecosystems. And the hope for us as biologists and marine researchers is that more and more countries will agree to not disturb these ecosystems until we have a better idea of which ones might be less destructive than others. Okay, last few slides before we get to the music. Why should we care? Researchers in most of the world are funded from taxpayer money. These are taxes where people work hard to let us play with little teeny tiny worms or go to the bottom of the sea. So why do these symbioses matter? And one of the things that we're finding is it doesn't matter if you are a symbiotic bacterium in a deep sea mussel or in a tube worm or in your own gut. we thrive from the symbiotic bacteria that we have in our gut. If we didn't have symbiotic bacteria in our gut, we couldn't digest our food. It's a nightmare for people that when you take antibiotics, I'm sure you know that it takes a long time for your digestive system to get back to normal. That's because you're killing all of those beneficial bacteria that are inside of you and that are good for maintaining your health and your well-being. So, all plants and all animals, including humans, are not alone. We are enveloped in a realm of symbiotic and beneficial bacteria that are essential for our health and for our well-being. And the incredible diversity of species that we have on our planet did not evolve solely through competition. Rather, it was cooperation and collaboration between different species that also made a very large contribution to the diversity of life as we see it on Earth today. This is my group, and the symbiotic relationship that we have in the research that we do. And I'd now also like to thank my student, Hiro Fuentes from Chile, who not helped, he actually translated the slides for me. So I'm very grateful to him. And also, he's a fantastic researcher. We now come to the music part of today's presentation. I think all of you know that, or as a researcher, I have to care about the facts and I have to be analytical. But there's not a single researcher on Earth that doesn't understand also that you have an emotional relationship to the organisms you work on or the environment that you work on. And so what I will be presenting here together with the musicians, the pianist Sten Ulloa Carler and the violinist Catalina Vergara, is a piece that was written by an Estonian researcher that I cut together with a documentarist from film material that we have from the deep sea. Please. So once again, this worked beautifully before all of you walked in here. But I'm sure we'll manage to get it going. Yay! Bravo, bravo. Thank you. That was wonderful. Thank you. I'm sorry.